Let's take another look at the antiderivative shortcut, as I would often call it at this stage, and how it's really the fundamental theorem of calculus, at least half of it, and then it can be made into the other half. So remember, the motivating problem here, it's a very specific physical problem, but I'm going to claim that it really can be translated into any integration problem. And that's if you're given the velocity of some object, a particle or something, can you find the displacement from one time, say t equals a to t equals b? And we hopefully have convinced ourselves by looking at like what the rectangle method does, what a Riemann sum does for this, that this is really the integral of the velocity over time from a to b. And if you look at a net signed area calculation, or if you do a tabular kind of calculation, you can see that this mathematical notion of the integral is exactly calculating this displacement. It's a bunch of distance equals rate times time calculations. So that, I'm going to assume that's understood and believed. And then I just point out, as I do in some other videos, that we've already known how to do this problem. If I'd asked this problem a little while ago, given velocity, find displacement, we would use the antiderivative, if we could find it, which is a big if, to find the position function, and then just calculate the difference of two values of the position function. So let me do an example here two ways. I'm going to use the language of velocities and displacements, and then I'm going to streamline it into the notation we're going to use from now on for just the general integration problem where we use antiderivatives to do the problem. So suppose in the example v of t is like this quadratic function. We want the displacement from 2 to 5. I picked one where it starts out going in the negative direction. It turns around at about 3.6 looks like, and then goes in the positive direction. So when we look at the displacement from 2, this is 2, it doesn't mark it, but that's 2, from 2 to 5, we're going to get some partial cancellation, and I'm going to guess that the answer, it looks like this area is a little bit bigger than this, but it should mostly cancel out, and I think give a small positive answer for the overall displacement. And what do we do? Okay, this multi-step method we're going to turn into something very, very efficient is, well, what's the position function? Well, it's t cubed minus 4t squared minus 10t. Okay, and then, minus 10t. And we're almost done now. We just look at that at 5 minus s of 2. Okay, and so we're going to plug in 5 cubed minus 4 times 5 squared minus 10 times 5. Okay. Oh, and you might think, oh, I forgot the plus c. I'm going to put it in here, but it's pretty much the last time I'm ever going to put it in here because we'll see that it cancels. And that's a very, very general thing. Okay. And then what's the other one that's going to be with a 2? Let me just write it out a little bit more efficiently. 8 minus 16 minus 20 plus c. Okay. And the plus c's are going to cancel out. And we're going to get, so what is this? This is 125 minus 100 minus 50 minus 8 minus 36. That is a minus 28. And we're getting minus, oh yeah, it's very close, minus 25 plus 28, yeah. That's what I remembered. It's just really close to canceling out. So we get 3 for the total answer. These plus c's canceled out. They always will, and that's why we're not going to write them anymore. And we're just taking the difference of two values of the antiderivative. Okay, we're just done. Okay, so what do we got here? We found that we can say the integral from 2 to 5 of this function, 3t squared minus 8t minus 10, I keep miskeying that, sorry, dt, and that dt is going to be a very important operational part of the story here pretty soon. So don't be lazy and don't write that. So 3t squared minus 8t minus 10, we are integrating that function. And what did we find? It was the difference of two values of an antiderivative. So let me just write out how does that get written out in a very efficient fashion. In a way that we don't have to assume it's a velocity and displacement problem, in a way where we can streamline this kind of steps, although this wasn't super hard, but it's nice to streamline it as much as possible. Okay, so now suppose somebody just gives you this problem as a pure mathematical problem, no interpretation about velocity, acceleration, position, blah, 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 displacement. It's still mathematically exactly equivalent to the problem we just did. And this idea will still apply, that integral can be calculated as a difference of two values of an antiderivative. And here's a notation that we use for that. We're going to put the antiderivative in square brackets. So we're going to have x cubed. So notice I'm changing to x to emphasize that there was nothing special about thinking about this as a time. And if this variable is x, we're going to use x here. And so we're going to put this in brackets, and we usually use square brackets here, not parentheses. And then we're just going to decorate this right-hand bracket very much in the way that the integral was decorated, with a superscript 5 and a subscript 2. Okay, and that notation is means that we're going to evaluate this function at 5 and 2 and subtract. It's exactly going to be what we did here, but without even actually mentioning the plus c's. Okay, so I'm just going to copy that down. Actually, let me make this displayed. So what this means is simply, if you've got any function, any formula, and you've got a number here and a number here, you plug in the numbers, the number on the top for x and evaluate the function. You plug in the number on the bottom for x, you evaluate the function, and you subtract. Okay. Another way to write this is you also might use regular parentheses, and then we do what's called an evaluation bar. Okay. Or you might not even use parentheses at all. I often like to have sort of parentheses just to make sure. So I'm going to put parentheses back, and then what we often do is let me put it in here. Well, let me see if I can move this. Need to get a thing out of the... Okay, that was a little awkward with the recording thing. So this is what we would call an evaluation bar. You just put this vertical bar to the right of your function and decorate it with the numbers. Okay, so very tight. This just exactly says to do this integral, we write down the antiderivative, we evaluate it at two numbers, the ends of the interval, and we subtract, and we get the answer. Okay, so that's the efficient way to write it out. And so that is one version of the fundamental theorem of calculus. There's really two sides to it, and this is what Stewart actually does is the second part of FTC. He likes to do it backwards from the way I'm doing it here. And it says you can calculate a definite integral using an antiderivative. The other part of this reverses the idea and says that if we create a new function, just briefly, a new function from an old one using a definite integral, and that's just brings in one slightly tricky bit, then this is also an antiderivative of what we started with. In other words, its derivative is the original function. So we're going to do that in another video or perhaps in class. But this gets us really on the board. This gets us really on the board where we can start calculating these integrals much, much more efficiently, as long as we can do this first step, which is finding the antiderivative, which means we need to get better and better and better at that process.